break. So last time we talked about continuous versus discontinuous, and the like easy definition is continuous means it meets up, discontinuous means there's a gap. Do you remember talking about that? Okay. Now we're going to talk about the types of discontinuities, and there's two of them. We have what's called removable or non-removable. And I left some space there because I'm going to draw you some pictures of like examples of what each of them are. Removable means everything in math kind of is exactly what it sounds like, because mathematicians are not very creative people. Everything just is what it sounds like, or it's named after the person that came up with it. Do you know what I'm saying? Like Pythagoreans. So removable means you just removed a point, and you could fix it and make it continuous again if you could just put that point back. So all you did was just like take a point out. So it would be something like this. That would be removable. I just removed the point. Following me there? It's not like a real difficult concept. The other way that that can look is, and I don't know if you remember this with the little floating point, the point that was kind of like floating out in space. I call this the na tricked you, the point's over here. Now, you can either just have a hole, or you could have a hole where the point is actually somewhere else. But the point is, if you could put that point back, it would fix it. That's what's called removable. Non-removable is a more deep-seated issue. You can't fix it and make it connect again just by putting one point back. So this would be something like a jump. So if you had something like that, you can't reconnect that just by putting one point back in. And then there's another type of non-removable discontinuity. Think of your rational graph, because that's discontinuous. What does a rational graph have in it that causes it to not like? An asymptote is the other non-removable discontinuity. You can't fix that. That's a really deep problem there. You can't fix that and make it reconnect just by putting a point back in there. That's not going to work. So we're going to practice graphing these again. Some people like to do the whole graph and then just erase the part they don't want. I tend to just like graph up until the cut point. The only point you have to worry about the, oh, bless you, the open or closed circle, bless you, is the cut point, okay? Everything else is just, they're all filled in. They're all just points, okay? And I also want us to talk about domain and range. I think I wrote that on there. We're going to state the domain and range and any discontinuities, right? So let's look just at this first piece. I'll zoom in some more. What kind of graph is that going to be? Quadratic. And how did it like shift and get like up 6 and it's flipped? So it's going to be upside down, all right? So like envision that. Use your imagination. We're going to go up 6. Put a point, and it's going to be upside down. I only want to graph it up until the cut point. Do you remember with the flip book where we actually took scissors and cut it? We're not going to cut this piece of paper apart, but where would that cut happen? At 2. All right, so let's plug in some more points. Like we're centered here at 0, but let's pick some points around 0. Like 1 would be a good point to plug in. And if you can do this in your head, you don't have to make a table. I just do this so you can see a little plug in. All right, here we go. 1 squared. 1, but it is -1 plus 6 is 5. So we get 1, 5. And if you know that it's going to be a parabola, you get the symmetric point. And then I'm going to go one further because I need to get all the way over to 2. Just pick up where we are. I'll give you this when we're done. Because then you won't like constantly be trying to catch up. Is 2 going to get a closed or an open circle? Closed, because there's that equal to. All right, so let's plug in 2. 2 squared. 4, but it is -4 plus 6 is 2. So 2, 2, closed circle, symmetric point on the other side because symmetry. And it's going to look like this. So again, it's like a graph that you just amputated. I feel bad saying that because that sounds sort of violent, but like it's a graph where you just cut off part of it. It's a piece of a graph. That's why it's called piecewise. Or like a piece of cake that we cut. That is less violent. We'll call it that instead. We like cake? There you go. Or pie if you don't like cake. Okay, good call. All right, what is this graph? What type of graph is it? It's not rational. It's linear with a slope of 1/2. Now, everybody was saying rational. I'm glad you said that. Let me clarify that. if the variable was in the fraction, like it was this, that would make it rational. Do you see what I'm saying? It's a very subtle difference, okay? But this is just a 1/2 x. So what we're gonna do is start at the cut point. But Miss Cole, you can't plug in 2. Yes, you can. But you will put what? A hole, an open circle. But you do want to plug in 2, and then we'll go up 1/2 for our slope of 1/2, okay? So if you plug in 2, what is 1/2 of 2? 1. So at 2, 1, you're gonna put an open circle. And then just do your slope of 1/2. It's up 1/2, up 1/2. It's gonna look kind of like a clock hand. And so we're gonna say continuous or discontinuous, and I want us to say removable or non-removable now that we're talking about that. And then we're just gonna do the domain and range just for like added fun. What's that? It is non-removable. You can't fix it just by putting a point back in there. There's an actual gap, all right? So we are gonna say non-removable discontinuity, and you wanna say where it happens. So non-removable discontinuity, you can abbreviate, whatever. I'm not grading your spelling or whatever. At x equals, and where did the jump like occur? At 2. And then I just want us to do domain and range for good measure, because I just believe you can do it. All right, watch me draw my pencil along here. Scanning, domain, left to right. Does it go left forever? I know that's pointing down, but it's gonna like, yeah, and it's gonna go right forever. And doesn't this piece pick up where that one left off? It's like as you scan left to right, do you lose anything? No. So negative infinity to positive infinity. There are no missing values. Range, I think same thing is going to happen. Do you see how it goes downwards and upwards forever? As you scan, you don't lose anything, right? Because I know everyone's like, look, there's a hole here, but don't we still get that value, that y value over here? Like as you scan, you get everything. I don't know, in my brain, this is like, welcome to my internal monologue. Do you know like in like a spy movie where they like scan? Like, I don't know, it's like scanning, or like a radar. I don't know, in my head, that's what happens. Like scanning. All right, cool, we did it. Let's try another one. 4, you kind of catch a break there. What is that gonna look like? Horizontal line at 4, and you just wanna stop at -3. Like here's where the cut would be happening. Like if don't actually cut the paper apart, but like here's where that would happen. And it would have what kind of circle? Closed. So we're gonna have a flat line here at 4, but just stop when you get to -3 and put a closed circle. Again, it looks kind of like a clock hand. Although, does anyone use an analog clock? Anyone do? Just for aesthetics. Well, I would agree. I mean, digital clocks are just more accurate, right? Yeah, easier. All right, what is this one gonna look like? The middle one here. Absolute value, and it shifted left to right. It's kind of backwards. Went right 1. So what we're gonna do is go right 1, put a point. That's where the center of the V is. Now, did it get stretched or shrunk? Oh, I took away my slinky. Did it get stretched or shrunk at all? No, so you can use 1 as your slope on either side. It's gonna go up 1/1, like both ways. And we just only wanna go from -3 to 2. Now watch what happens. When I go up 1/1 this way, oh my gosh, it connects. Do you see that? I know that is crazy. It is cute. And when you go the other way, you're only gonna go as far as 2. So it gets cut off. The slice of cake or pie got cut off there. And why did I put a closed circle on the 2? That thing, right? Like the equal to? Okay, good. It's fine. I'm not going to yank you in the hall and make you take a verbal exam. Okay. All right, and then square root. You are still going, oh, I forgot to add, what kind of graph is this? Square root, good job, I just said it. I'm going to make a little table of values. You're still going to plug in 2. You will just put an open circle. You're still allowed to plug in 2. Just put an open circle, all right? Here we go. 2 times 2, 4. Square root of 4 is 2. So 2 gets an open circle. Bummer, those ones didn't connect. I know, right? Now, think about it. I'm going to be quiet and let your brain work. You need to, I think, go out quite a ways until you get the next number that's going to like work out that will actually be able to plug in. But think about it. Try like in your brain 3, 4, 5, 6, 7, until you get something that's gonna work. Put that in a backpack. Do we think 8? Let's see. 8 times 2. Good. Square root of 16 is 4. So 8, 4. I think that's right on the edge of the grid, right? Now, I usually require 3 points, but I mean, that's good enough. It's going to do something like that. Yeah, I mean, you'd be off the grid there. But that's true. For the whole graph, we have way more than 3 points. Isn't that one cool? That one looks kind of cute. Let me clarify. Do you see how this is constant? That's just going to stay at 4 forever. This one is going to keep on going up forever. Like, I know it's looking very lazy, but that arrow indicates it's going to keep going, and it will keep on going up. It's just like way off the page. All right, continuous or discontinuous? All right, and what kind of discontinuity is that? Can you fix it just by putting a point back in? No, so it is non-removable. Good. Non-removable discontinuity at x equals 2. Good. Non-removable discontinuity at x equals 2. I know, like, big vocabulary here. Welcome to advanced mathematics. You've arrived. And then I just want to do domain and range. So domain, scanning left to right. Hey guys, just watch. I'll just drag my pencil across the paper. Scanning, 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 scanning. Do we lose anything? No, that piece picks up where that one left off, so we get it all. Yay. Range is not going to be all reals for this one. And again, just watch me drag the pencil along the paper. There's nothing down here. What y value do we start at? 0. And there is actually a point there, so we will put a bracket. 0. And then, as I just talked about, isn't this going to keep on going upwards forever? I know it's not like in a great big hurry, but it's headed that direction, so it will keep going. Infinity always gets a parenthesis. It's not a value, so you can't like include it. We'll do one more and I'll give you a break. What kind of graph is this one? Exponential. Did it get shifted around at all? Hey, are you awake over there? Yeah, heads up. So that means the asymptote is still on 0. So I know you can't really see it because it's on 0. Doing my best here. All right, because it didn't get shifted up or down. Let's try and plug in some values. I would start with 0. I think that's the easiest number to plug in. Here we go. 2 to the 0. 1. What else do you want to try and plug in? Let's do 1. 2 to the first is 2. So you get 1, 2. And I would like one more. Or, oh, wait, we can't go any further, can we? Shoot, I was ready to graph the whole thing. Let me back up. That point at 1 is going to have to be what? A donut? Let's go with open circle. Sorry, I was ready to just keep going and graph the whole thing. I like exponential graphs. They're my favorites. I got excited. I was like, oh, swoop. All right, so we only get this part of the swoop. Absolute values, cool too. If you like the greatest integer one, you might be the first person to ever say that. All right, now this one, we're still gonna plug in 1, but again, it's gonna be an open circle because there's not an equal to, right? So if we plug in 1 for that, what will we get? If you plug in 1 for x, that'll be -1 plus 3, 2. Isn't that right here? Okay, but it's still an open circle because see, neither of them has an equal to on it. And what's the slope of this line? This one's linear, not 1, but -1. So you're going to go down 1 over 1 from that open circle. Do you see how it's -1x plus 3? Like the y-intercept would be at 3? Like, I don't know. Are you guys getting that? Like if we kept this line going and graphed the whole line, do you see how it would intersect here at 3? Like up 3? Just we chop that part off. Anyway, removable or non-removable? That one's removable. You could fix it if you could just fill that circle back in. So removable discontinuity at x equals 1. Good. We just like took the point out. Someone just stole it. I know, right? And then I just want us to do domain and range. All right, domain, look it. Scanning left to right. We get it all except for what value? 1. How do we leave out 1? We did ones like this last time with the rational graphs. I'll give you a hint. It starts with negative infinity to not 0, but 1, bracket or parenthesis. You want to leave it out. Parenthesis, good. And then union 1 to infinity. What you're saying is you want everything to the left of 1, everything to the right of 1, but not 1. You're leaving 1 out. All right, range, scanning downwards to upwards. Hey, look, we have everything. So starting, negative infinity, downwards forever, up until what's the peak, like y value we get to? 2, but can I include it? No, there is an open circle there. So that is what a removable discontinuity is. All right, take your 2 to 3 minute mobile device break and we'll do the back. All right, so for this one, that is just the function y equals x. It's gonna look like this. It'll go through the origin, have a slope of 1. We wanna graph it everywhere except 3. Like when it says, you like the no parking sign, like the equals with a line to, you wanna graph it everywhere except at that point. So here's what I would do. I would just graph the line. Like we're gonna start at the origin, slope is 1, just go up 1 over 1. Like just graph the whole line, because I think that's easiest. If you're writing with pen though, don't. I'm not gonna say don't use pen in math classes, just sometimes it's not advisable. Now here, watch. I'm just gonna erase the points at 3. Watch, I'm gonna count over here. 1, 2, 3. Here's 3. I'm gonna go to that point on the graph and I'm just going to erase it out. I'm just stealing it. So now it's aligned with a hole in it. We just removed that point. So heads up, it's gonna be a removable discontinuity. Literally just removed it. Now this is like, nah, I tricked you. I stole the point and stuck it somewhere else. Look at the next part. When x is 3, where do I want to put that point? -2. So I'm going to come down here to -2 and put that point there. Like the floating in space. I kind of like those ones. Point that's just like floating out there. Cute. Yeah, like it just like fell out and now it's down there. All right, so anyway, it is a removable discontinuity at x equals 3. Because we just removed it and stuck it somewhere else. And then we're going to do domain and range. Because I said so. So scanning left to right, do you get everything? You do, right? Because I know that this point got stolen, but it's somewhere else. So it still exists. So as you go left to right, you actually get everything. Because left to right, there's still a point at 3. It's somewhere else, but it still exists. Now, scanning downwards to upwards, watch. As I scan downwards to upwards, I actually am missing like a y value there. Like when you go left to right, you still catch it, like you still scan it that way. When you go downwards to upwards, that value's missing. What value are we missing for y? 3. You want to leave out 3. So you want everybody except 3. Everyone is invited to the range party except 3. So we want everything smaller than 3, everything bigger than 3, but not 3. So make sure you use parentheses. I call them the troublemakers. When we get to that unit, the rational unit, I'm like, the troublemakers, pick them out. All right, 5, A, B, and C. Weirdly, this usually goes better for everybody, which I find funny because I think it's actually harder. But I think people just like not having to actually graph anything. I'm going to give you the graph. I want you to write the equation. Okay, so I have space down here for this. We're just going to label A, B, and C. So we're going to write a function. And yeah, you need to do a swirly bracket. If you can't draw a swirly bracket, that's okay. Just draw like a squiggle. I don't care. Whatever. And you're just going to write an equation for each piece of the function. So look at A. What kind of function is this? Good, so there's gonna be a squared. What direction did it shift? Left, which is gonna go inside the parentheses and it's kind of backwards. So it'll be positive, good. And also it is upside down, so we need a negative. Awesome. All right, so it's negative, and then what do we go? Left 3, so x plus 3 squared. You are just writing an equation for that graph. That is all it is. Now, off to the side, we need to say where the domain is. So where did our cut value happen? Like if we were going to cut this, where did that happen? At -1, and do you see how it's an open circle there? So we want it x less than -1. Everything smaller than -1. What kind of graph is the other one, the other piece of that? So linear, what is the slope? And you can draw in like some of the lines if you want to like see how much up and over it goes. 1/2, I heard somebody say it over there. Do you see 1/2? So it's going to be 1/2 x, and then where's our y-intercept here? Where's our y-intercept, guys? -5. Good. Y equals mx plus b. It's 1/2 x minus 5. But we only want to define it where? How would we write this? Greater than and equal to, good, -1. Equal to, because there's the closed circle there. Just pick up where we are. Yeah, okay. All right, this one's broken into 3 pieces. So put f of x equals, draw yourself a swirly bracket. What kind of function is the first one? Absolute value. It moved, what did it do? Left 4, down 1. It did not get stretched or shrunk at all. Do you see how the slope of each side is still 1? Like it's just up 1 over 1. All right, so it's going to be absolute value. What will go inside it? Remember, left and right's kind of backwards. Good. X plus 4. And then outside of the absolute value would be -1. Then off to the side, where do you want to define that when x is what? Look at where the cut is going to happen. Negative, when x is what? Less than, oh good, or equal to. Less than or equal to -2. Equal to, because it has the closed circle. Now you kind of catch a break with the middle part because it's constant. It's literally just going to be what? -2, just a flat line at negative, like it's literally just the number -2. That's all that is. Now, this is a little tricky when it's the in-between piece. We want it to be from -2 until 3. So from -2 to 3. So what I usually do is write it like that, like -2 to 3, x is going to be in the middle. And your little alligators are going to eat left to right, if you want to remember it that way. I don't know, however is best for you to remember. Usually what you can do, honestly, like on a test situation, is go back and find another problem that had one like this and kind of just, do you ever do that? Like use the test to like help you do other problems? Anyway, we don't want to include the -2, but we do want to include the 3. And then that last piece, again, it's linear. We want to do y equals mx plus b. So what is the slope for that? Slope of this line? -1. So -1x plus, now you want where the y-intercept would be. Look at this. I know it's not on here, but if you were to continue this, where would it hit the y-axis? Like if you continued that on, 3, right? I know it's like not there. You kind of have to imagine it. Like just what would happen if you continued that on? So y equals mx plus b, -x plus 3. And we want to define that x is where? Greater than 3. Good. Greater than, because it's an open circle. Last one of these. Do you see how this one is going to be a lot like number 4 that we did up here? Like where you just took the point and put it somewhere else? Again, just like use what's already on the paper to help you.
First, let's do the flat line. That's just a flat line at -2. Like it's literally just -2. Now, where is that defined? Everywhere except -1. So x not equal to -1. It's like the no parking sign. It's everybody except -1. And then where did we stick the point? We stole it and we put it where? At +2. And what will we put for that? Yeah, x equals -1. So it's like one rule for -1 and a different rule for everywhere else. Now these last two, find A, this is algebra here. So if you're more of an algebra person than a graphing person, you'll like these. We want the function to be continuous. All right, this is common sense. If you want the two pieces to meet up, what should you do with their equations? If you want them to link up, make them equal each other, okay? That's literally all you're gonna do. You're gonna take this piece and make it equal this piece. 5x squared plus a equals 3x. You set them equal. You want them to link up, set them equal. Now we want them to link up at what x number? Everywhere there's an x, you guys are fading on me. We have two questions. You can do it. Everywhere there's an x, you're gonna plug in a -3, all right? So everywhere that there is an x, put a -3 and give them all hugs. Hugs for all of them. And then we're just gonna solve it. Some people don't like graphing. They're more of like an algebra person, like you just want to do steps. Like a lot of people at this upper level are kind of like that. You'll like these better than. All right, -3 squared. +9, good, times 5, 40, perfect, plus a equals -9. And you would subtract 45 to the other side. So if you subtract over 45, let's see, here I'll write in the -45, -45. -9 and then -45, that'll be -54. Well, count on your fingers, that's all you got. 9? No, 9? But 45, 46, 47, 48, 49, 50. Do you not watch PBS, kids? Oh, what is that? Isn't that what like Arthur was on and stuff? Okay. Okay. All right, we want to set them equal. You want it to be continuous. Take this and make it equal this. 2a squared plus x equals 3x plus 7a. Made this one a little bit of a tougher problem, but I believe in you. It's the last one though, so wake up. After this, we're going to be like pretty much finished. Now, you want them to be equal when x equals 2. So everywhere there is an x, you're going to put a 2. Everywhere there is an x, you are going to put a 2. Not the a's. A is what you're trying to solve for. So let's kind of clean that up a little bit. 2a squared plus 2 equals what? 6 plus 7a. This is more of an algebra 2 type of problem because of the squared in it. Whenever there's a squared, I call this evacuate, evacuate. Hit it all to one side so that it equals 0. Do you remember doing this last year in algebra 2? You did it. I call it evacuate. Get everybody to one side so it all equals 0, okay? So if you subtract over the 7a, that'll be 2a squared minus 7a. And then if you also subtract over the 6, 2 minus 6 will be -4. Do you guys remember doing that? What did your teacher call it? I call it evacuate. Did they call it anything? Like, oh, just make it equal 0. Just do it. Okay, I call it evacuate. When you see a squared, evacuate. Everybody get out. Get to the other side. Now, the reason this is a tougher problem is because it involves factoring. So we're going to see what you got. Oh, no, it's going to be okay. Don't do that to me. You learned it last year and you're going to be totally okay. What numbers multiply together to equal 2, children? 2 and 1. Okay, so it's going to be 2a and 1a. We're just breaking that apart. 2 times 1 is 2 is literally all we did. Nothing scary, okay? Now you're going to look at the 4. What multiplies together to equal 4? 2 times 2 or 4 times 1. Now, for the sake of us getting through this, I'm going to go ahead and tell you it's the 1 and the 4, but you would just try something and see if it works. And if it doesn't, you will do try again. That's how it works, okay? Watch. What do the outsides give you if you multiply these two? 8a and the insides, 1a. Will 8 and 1 give you 7? Oh my gosh, now we want it to be a -7. So you want a -8, 2 times -4 will be -8, plus 1 will give you -7. It is just try. Look, you all survived. Now you need the actual answer. So you're going to set each of these equal to 0. We'll do this one first because it's easier. If you set a minus 4 equal to 0, what will you get? 4, because 4 minus 4 is 0. And if you set 2a plus 1 equal to 0, what would you get? You'd have to subtract the 1. Good, -1/2. I don't know who said that over here, but nice job. High five.